All right, today we're heading right into the heart of a massive ship's engine room. Why? Because we're going to decode a secret language. It's this vital electrical signal that basically tells engineers everything they need to know to keep these absolute giants of the sea running safely. So let's just dive right in with a question. I want you to imagine something. You're a marine engineer, and you are responsible for an engine the size of a small house. Seriously. So how on earth do you know if just one of its massive cylinders is starting to have a problem?
I mean, it's not like you can just pop the hood, right? You can't actually see the combustion happening deep inside. And the noise, over that incredible, deafening roar, there's just no way you can hear the tiny, subtle sounds of a single part starting to fail. So, what do?
Well, you listen, but not with your ears. You listen with instruments. You see, the engine speaks a kind of silent language. It's a simple electrical current that tells you pretty much everything you need to know about its health. And that language? That's the 4 to 20 milliamp signal.
Okay, so let's become translators. In this first part, we're going to decode that signal. We're going to figure out exactly how the raw, incredible heat from combustion gets turned into data that an engineer can actually use. And you know what? It's a beautifully simple process, really. Just 3 steps. Step 1, you've got a sensor, something like a thermocouple or an RTD, and its whole job is to measure the exhaust gas temperature for each and every cylinder. Then, step 2, a transmitter takes that temperature reading and translates it. It converts it into an electrical current that's perfectly proportional, somewhere between 4 and 20 milliamps. And finally, step 3, that signal gets zapped over to the nice, quiet, safe engine control room, where it pops up on the monitoring systems for the engineer to see.
And here it is. This is basically the code book. This is how we translate that signal. So let's assume the system is set for a range from 0 up to 500 degrees Celsius. The relationship is it's perfectly linear. At the bottom, 4 milliamps means 0 degrees. At the very top, 20 milliamps means the maximum, 500 degrees. And everything in between? It's a perfect 1-to-1 scale. So if you see 12 milliamps, that's exactly halfway, which means 250 degrees. It's simple, it's elegant, and it is incredibly effective.
Okay, time to put our new code-breaking skills to the test. Let's open our first case file. We've just gotten a signal, and it's indicating a low temperature. Now, that might not sound super dangerous, but trust me, it points to what's called a silent cylinder, and that means one cylinder just isn't pulling its weight.
And here's our first piece of evidence. The monitor is showing a reading of just 6 milliamps from one of the cylinders. Now, if we look back at our code book, we can do some quick math, and that translates to a temperature of only about 62.5 degrees Celsius. For an engine cylinder exhaust, that is really low.
So, what's going on here? What could be causing this? Well, we have a list of the usual suspects. It could be that the cylinder is misfiring, or maybe there's poor fuel injection. Could be a problem with the injector itself. You might even have a valve that's leaking. Or, hey, maybe it's simpler. The engine is just running on a very, very low load. Each one of these possibilities has to be checked out.
But why does this even matter? I mean, a low temperature, what's the big deal? Well, the big deal is that a cylinder with a low exhaust temp isn't actually contributing any power. It's basically a freeloader, just along for the ride. And that creates a serious imbalance in the engine. It puts all this uneven stress and load on the other parts, the ones that are still working hard. And, of course, your fuel consumption is going to go way up.
All right, let's move on to our next case file. And this one is much more urgent. We're talking about a high-temperature reading. This isn't a quiet signal. This is a screaming alarm that the engine is heading into the danger zone.
Okay, the evidence comes in hot, 18 milliamps. A quick calculation tells us we're at 87.5% of our total range, and that translates to a blistering 437.5 degrees Celsius. We are getting very, very close to a critical limit here.
And the list of possible causes here is, well, it's pretty serious. We could be looking at the whole engine being overloaded. Maybe the cooling system is failing. It could be something like late injection timing or even a dirty, clogged-up turbocharger. Every single one of these points to a major problem that needs attention right now.
And the consequences? Oh, they can be catastrophic. A temperature this high can literally burn out your exhaust valves. It can damage the piston crowns. It could cause the turbocharger to fail completely. This is exactly why the alarm systems are set to go off around 450 degrees, and if it gets near 500, an automatic engine trip or shutdown is triggered. The system will literally shut itself down to prevent a total meltdown.
Okay, before we wrap this up, there's one more secret to this language that we absolutely have to talk about. It's a truly brilliant piece of engineering called the live zero.
and it solves a huge, potentially critical problem of, well, getting it wrong. This is where the true genius of the system shines through. Just think about it for a second. What if the scale started at 0 milliamps? If you saw a reading of 0 on your screen, it could mean two completely different things, right? It could mean the engine part is actually at 0 degrees, or it could mean the wire's broken. How would you know the difference? You wouldn't. But by making 4 milliamps the live 0, the system becomes basically foolproof. Now, a 4 milliamp signal means, yep, I'm reading a valid 0 degrees and I'm working fine. And a reading of 0 milliamps, that can only mean one thing: there's a fault. The wire is broken, the sensor failed, something's wrong with the system. It is such a simple but brilliant safety feature.
Okay, so let's head back to the engine control room for a minute. Let's see how a real engineer puts all of these clues together to make a final call, a verdict on the engine's health.
Just picture the scene, right? The engineer is scanning the bank of monitors. All the cylinders are just humming along, everything's looking good. Temperatures are sitting right around 350 degrees Celsius. It's a normal day. Everything looks fine.
But then their eye catches it. One number, one reading that's just off. One cylinder is showing a reading of 19 milliamps. And they know instantly what that means. That's nearly 470 degrees Celsius. It's way, way hotter than all the others. And that single number, that is a clear, undeniable cry for help coming from that one specific cylinder.
And really, this is what it's all about. This is the whole point. Without this simple, silent 4 to 20 milliamp signal, really severe, incredibly expensive, and potentially dangerous damage could happen to that cylinder long before any other sign was visible or any strange sound was audible over the engine's roar.
So, in the end, it really comes down to this powerful idea. When you're an engineer and you're looking at those numbers on a screen, you're not just looking at data. You're hearing the health of the combustion happening deep inside that machine. Instrumentation truly is the voice of the engine. And the 4 to 20 milliamp signal, that's the language it speaks. And the job of the engineer is simple: to listen, very, very carefully.